Hello, and welcome to How a Rideshare Giant Uses Artificial Intelligence to Detect Business Anomalies. My name is Chris Screenack, Machine Learning Segment Lead for Amazon Web Services, and I will be your host and moderator for today's presentation. In addition to learning about AWS, you will also hear from Ira Cohen, Chief Data Scientist and co-founder of Anodot, and Gleb Majonski, Product Manager of Data at Lyft. In this webinar, you will learn how you can use AI within your AWS environment to find anomalies in large data sets quickly without relying on manual dashboard inspections, how to deploy an AI solution on AWS that creates instant alerts as well as robust metrics dashboards for daily data analysis tasks, and how AWS and Anodot provide organizations with a secure framework for anomaly detection. And remember, please post your questions in the chat bot throughout this presentation, as we will review questions at the end of today's event. So let's start with AWS. At Amazon, we've been making investments in machine learning for more than 20 years. This is through both our fulfillment and logistics, search and discovery, many existing products, and it's spawned the creation of new products as well. Our objective now is to put that expertise in machine learning and artificial intelligence into the hands of every developer and data scientist. The market adoption of machine learning is enormous and pervasive. There is a strong appetite for adopting AI across the board. Currently, most of the innovation is happening in high-tech industries due to the familiarity with some of the early technologies. However, opportunities exist virtually across the board, especially in areas such as healthcare, retail, education, media, and entertainment. And there are more than 3,000 startups today, up from 100 in 2011. We, once again, have a very long heritage of machine learning at Amazon. Many folks are very familiar with our personalized recommendations that are available on every screen at the Amazon online store. Also, our fulfillment and automation services have been highly automated with the advent of Kiva robots that will move around our warehouses and dramatically accelerate our ability to fulfill orders. We're also working with drones in the fulfillment of orders with Amazon Prime Air. And also, the innovations have led to many voice-driven interactions, especially with Alexa. We also have, and there's only one now at this point, introduced in an entirely new way of shopping, where with the Amazon Go store. When you walk into the store, you just scan your phone, you choose what you want, and frankly, it feels like shoplifting until you walk out of the store and you immediately get a notification on the phone that you've been charged $6 for a sandwich or whatever it is that you just picked up in that store. So famously, the new product lines that we have in the Amazon Echo and Alexa, which are expanding now to products in business, have been flagship products for us in machine learning and artificial intelligence. Amazon Recognition Video has brought the breakthroughs in computer vision, not only in still images, but in video images, to a whole new class of applications with object identification, person tracking, facial recognition, which is all available through real-time live streaming, and also being able to process remotely through products like Deep Lens. We also provide content moderation and celebrity recognition as well. Here's an example of a real-time analysis of not only events and objects, but you can also use this for doing two-factor authentication and many other use cases. This is all part of what we call the Amazon Machine Learning Stack, which is sort of a cake structure where the icing on the cake are these REST-based application services. They are principally through vision and language, as I mentioned with recognition, for computer video. But in speech and language, we also have services such as Amazon Polly and Lex, and Amazon Transcribe, Translate, and Comprehend, which add new dimensions to natural language processing that do not require any expertise in data science. They are simply REST-based calls and managed services. Underneath that layer of the cake, we have our fastly growing platform, SageMaker, which is the first end-to-end machine learning development platform, which takes all ideas literally from inception to global deployment, often with single key clicks. On the bottom of this layer, we have the strongest GPU instances on the planet with the NVIDIA Voltas, our P3 instances. We also have IoT and mobile services to deliver machine learning algorithms to both devices out in the field and to your mobile phone. Just about everybody's running some form of machine learning on AWS. The customer list is extraordinary, and we're very eager always to hear what your use cases are, because the #1 key at Amazon is what your interests are, and we're endeavoring always to listen very, very carefully to what your needs are. Finally, at the top of our service stack, we have the machine learning competency. The machine learning competency is a strict program where we work with our partners, pick the absolute best of the pack, do complete, well-architected reviews, and analyze their software to make sure that it not only represents the state of the art, but that it is also robust enough to handle the kind of traffic and the kind of services that our AWS customers expect. And now, with that, I would like to introduce Ira Cohen, Chief Scientist and co-founder of Anodot.
Thank you, Chris. So I would like to introduce Anodot's Anomaly Detection and basically explain what we do and how we do it in the context of to set the stage for Gleb from Lyft to describe how they're using anomaly detection in their business. All right, so what is the state of things and where are we starting from? So everybody's well familiar with various business intelligence dashboards, business analytics dashboards, and visualizing data. And if we look at the history of how of analytics, actually what we see is, from the 1970s, we started building tools that gave visibility to executives using reports. In the 80s, we started having dashboards, but they were very limited. In the 90s, with databases coming out and the ability to slice and dice the data, you got agility around these dashboards, which was very nice for reporting. And really, in the new millennium, we started collecting real-time data, both for operational and speed, but we're still there with the dashboards to view them, and with very limited tools to actually be able to react to the data. So everything was very reactive and late. So what we see in this decade is that especially with the advances in big data and the ability to process large amounts of data very, very quickly, both collect and process, we're starting to get scale. But here is where the traditional tools that were started in the 80s, these dashboards and reporting, are actually very limited. You're looking at vast amount of data with a very, very, very small lens, which are these dashboards that show you, a very small fraction of what's in there. So here, this is where AI comes in, or machine learning comes in, being autonomous about the analytics. What does it mean? Let the machines look through the data and find out what's the insights automatically in the data, and highlight what's really relevant to view. And this is where a tool like Anodot comes in. One of the ways to find insights in the data is using anomaly detection. What is anomaly? What are anomalies? Anomalies are anything that looks out of the ordinary in the data. And why is that important? Because anomalies usually indicate either issues or opportunities, because they indicate something is strange happening, something is not normal happening in your vast amount of data, in your business data, and taking them and looking at those anomalies actually are the insights themselves that help you manage the business and be more agile. So I'm the data scientist, so I'm going to talk about a little bit of how we built an anomaly detection system and what we feel are the key requirements from such a system to be operational and provide a lot of value. So the way we think about anomaly detection is using these 5 steps. So anomalies by nature are the way you detect them is using unsupervised algorithms. So what we need, so because it's unsupervised, the only thing we can rely on is trying to model what is normal. So really the steps to find anomalies at very large scale is first to be able to collect a lot of data, but also analyze the data in real time as they're being collected. So being a system that can collect a lot of data and be scaled to millions of these time series is not just about the collection. That's a pretty solved problem, but it's also about the analysis of the data in real time. If you're able to do that, you can actually start processing and learn what is normal about the data. And once you find how to model what is normal, you can find anomalies. And then we found that you actually need to also model the anomalies themselves so you can rank, score, and classify them. And I'll show some examples later on. Then the 4th step is being able to understand the relationships between the anomalies. So let's say you're a business like Lyft or any other digital business. You're collecting a lot of these time series describing the performance of your business, like revenue, a number of rides, a number of people opening the app, a number of people crashing the app, number of drivers you have around. All of these measures, you can find anomalies in them, but if you don't know how to connect the dots between the anomalies, you're left with a lot of noise, and you don't know how to connect the dots. So that's another aspect that we found is really crucial to be able to learn the topology of the anomalies, how they're related to each other, and you can't rely on humans to tell you that topology. The last step is getting feedback from users. And what we found is that you can't assume you'll get feedback. So you can't assume this is a supervised learning problem. You have to assume this is unsupervised, but you can leverage small amounts of feedback that users are willing to give you either implicitly or explicitly to improve the performance of the algorithms and what they learned. So that's this 5th step. So let me drill down a little bit into these steps and describe them. So the first part is learning what is normal. So you're collecting a lot of different time series, and here are some examples of different types of time series that we see constantly in our environment. And they can have very different behaviors to them, which means that you have to apply different types of models and learning algorithms to actually learn the normalcy of each one of them. So some of these types, as I mentioned, all of them appear. A lot of the work that has been done in academia has dealt with the top left corner, what we call the smooth signals. Smooth signals are regularly sampled, stationary, sometimes ergodic, or can be made to be ergodic signals. And then you have various types of models that can capture what is normal about them, their normal patterns, fairly easily. But we found that those account for about 40% of the time series that companies collect. So what about the rest of the 60%? Do you leave them out or do you include them? And actually, if you leave them out, how do you know to leave them out? So you have to classify your signals anyways. So what we see is a lot of different types, like irregularly sampled data, which is completely normal, multimodal, sparse, discrete, step. And for each one, you actually have, if you want to be robust, you have to apply a different type of learning algorithm to capture what's normal about them. So this is just, it's a single, learning the normal behavior of a single KPI. So some of the challenges that you have to take into account when building such a system is being able to classify automatically what type of signals do I have, what's the right distribution to apply to the different signals, do they have seasonal patterns or not, and what type of seasonal patterns, you could have multiple seasonal patterns in a single KPI. And because we're dealing with businesses that keep changing, you have to have adaptive algorithms. You can't assume that everything is static. So if you're measuring something like an engine of a Boeing 747, you can assume that for 20 years, not a lot is going to change in that behavior of that engine. Or if it changes very, very slowly. But if you're measuring a business like Lyft or any other business, it's probably going to change week over week, sometimes day over day, and the changes are normal, and you have to have a system that adapts to them. Otherwise, it becomes very stale and unrobust. So these are the type of things that you have to take into account just to learn the normal behaviors of time series. The next step is really looking, once you learn the normal behavior, and here in the charts, you can actually see the solid line is the actual time series being measured, and the shaded area is what the output of the normal model, which says, for every point in time, where should the next data point be in? What's the range of the next data point? And if it's outside the normal range, it becomes an anomaly. So anomalies can be small or can be big, and they're not all the same. And so we have to have some sort of a abnormal model of anomalies to be able to rank and score them. Now, ranking and scoring them is not just about the statistics of the anomaly, meaning how much did it deviate from the normal pattern? Did it deviate by a lot or by a little? Because what we found from experience is that that's not by itself is not meaningful enough to rank and score anomalies. You really have to look at all the anomalies that were there and their patterns in terms of how long did they last and how much did they deviate compared to all past anomalies, so you can have some model of significance. So what is the significance? The more surprising the anomaly is, the more significant it is from the mathematical point of view, but also from often from the business point of view. So if I have a lot of anomalies that look like this anomaly marked with a significance score of 84 or a probability of 0.84, if I have a lot of them in my history, then it's not such a significant anomaly. It should get a lower score, a lower significance score. But if it's surprising enough that I haven't seen anything like it before, it should get a very high score. And that's really what we found is very useful for users using an anomaly detection system, giving them one lever, one knob to say, I want to see all anomalies for my revenue. If I'm looking at my entire company's revenue, I want to be very sensitive to any anomaly, even these small ones. But if I'm looking at my revenue per city or maybe a district, then maybe I don't need to be as sensitive, and I can say, show me only the anomalies with higher significance. And that's really the type of levers that let users that are not familiar with the algorithms still make such a system useful for them. So this is about this ranking and scoring, but there are other types of things that you want to look at when you're looking at anomalies. So one of the things we look at is classifying anomalies to different types of anomalies. So this is the most common type of anomaly, a transient anomaly. So you can see the anomaly here going out of the normal range in the far right, and basically, usually these are things that went wrong, and you want to fix them, and you want to bring things back into the normal range. But that's not all the types of anomalies that happen. Sometimes things change, they are anomalous, they change, and you want them to change. So you want to classify that anomaly as a pattern change, or in this case, a level change. So let's say I ran a big campaign to get more users to use my app, and now I see a bump in the number of users. So it's good for me to know that there is an anomaly. There was a bump in the number of users because it tells me my campaign worked fine. And I want to actually see the system adapt to a new pattern of behavior and tell me there was an anomaly of type level change that happened. So there are use cases where you want to know that. And of course, you want to know about trend changes, and you want to know about seasonal pattern changes. All of these examples are actual examples from our system that we've seen happening in practice. So here is an example metric that had a seasonal pattern, and then the seasonal pattern stopped for whatever reason. The next step is what we call the behavior topology learning, or really correlating between the anomalies so you can have a concise view of what's happening. So how do you actually do that? And how do you do that at a very high scale? So when you have millions of these time series or even billions of these time series. So again, the user doesn't necessarily tell you anything about what's related to what, and he might not even know that the revenue is related to some API errors that might be also being measured at the same time. So luckily we have data, and the data can tell us a lot about what's related to what, and we can learn that. So we actually employed three types of cues in the data that helps us figure out what is related to what to create a relationship graph between all the different KPIs. So we look at the metadata describing every single KPI. So the metadata is basically what am I measuring, like revenue, and where am I measuring at my revenue at? I'm measuring it in a certain city for a certain segment of my user base, and so on. So all of these metadata information actually allows us to apply similarity algorithms that will tell us are things similar enough. So, and if they are, we can group them. So that's an obvious one to use. But then you also have the actual the actual data that these measures produce, so that you can also glean some information about what's related. So abnormal-based similarity, what does that mean? So if I'm measuring my revenue and I'm also measuring a number of users that are using my app, these are two different KPIs, I can see whether they are related to each other based on their, do they tend to have anomalies together in the history? So if they become abnormal together, there's a high likelihood that they are related to each other. So here, if we look at the history of all these KPIs, find the anomalies, and then cluster them based on whether they overlap in their anomalies, we can find very interesting relationships between different different time series that are often not obvious. So they might look very different from each other. They might be measuring completely different things from different systems. But then when you do this type of analysis, you find that they have some relationship, basically because they come from the same ecosystem and they get affected by the same causes of anomalies. The last aspect is looking at the normal behavior. And here, trying kind of the normal algorithms like clustering or k-means or any type of linear correlations between time series usually doesn't work well. That's from our experience. So you can experiment with that, but you'll see that you get a lot of false positives, especially at high scale. So you have to do some compression of the data and then apply clustering algorithms on a compressed version of the data. Lastly, to make it all scalable, because these are fairly expensive algorithms computationally, we're using locality sensitive hashing throughout these algorithms to make sure that we can scale out and run on the millions and billions of time series that we need to run on and still produce meaningful results. So this is about how we do it. How did we actually architect the system? So as we mentioned, we actually built a system on AWS. So we run on AWS, and this is a high-level architecture of our system. Because, as I mentioned earlier, because we need to actually be very scalable and scale out to millions and be real time as well, we cannot afford to take the data, push it into a database, and then pull it out for finding anomalies in it. If we did that, we wouldn't be able to scale at all. So basically, we have to have online algorithms that continuously adapt and learn from every data point that comes along and find anomalies on the stream of data itself. Only after we find the anomalies and analyze the data, then we can store it for visualization purposes later on in our app, and I'll show a quick demo of it. So that's really the crux of how we have to do it. Once we find anomalies, we can actually push it through various queues to group them together based on the relationships that we found. And in our architecture, we use Cassandra as our data store. We use Elasticsearch to index metadata about the anomalies. We use Kafka for handling events, and we use S3 as our data warehouse, and Hadoop Spark Hive with EMR that AWS supplies to run some offline learning jobs that we don't have to run in real time on the stream itself. Not everything has to be run in real time. For example, clustering, we don't have to run on the stream itself and adapt with every data point. We can run a nightly job. It still has to be scalable and fast, but it doesn't have to be done in real time. So a little bit about some of the customers that we have. And let me step into that slide. So we've been around for almost 4 years, and I think Chris mentioned some of the early adapters also of the machine learning aspects in the industry, and you can see some of the leading names around. So Lyft, of course, and you'll hear about how they're using us, but Waze and Pandora Music and King and social and various ad tech. So King is mobile gaming, Candy Crush, and so on. So a lot of different types of businesses. Their main pain point is that they really need to move fast. They are very data driven, and by being data driven, they actually have to analyze the data, not just collect the data, and make rapid decisions, whether it's minute to minute, hour to hour, sometimes day to day, but still the volumes of data require an automatic analysis of all the of everything that happens inside. So with this, I'm going to stop, and if we have time at the end, I'll show a quick demo of our system. But I think I'm going to let Gleb from Lyft talk about their implementation of the solution within Lyft and why they actually did it and how they did it. So thank you very much.
Thank you, Ira. Hello, everyone. My name is Gleb. I'm product manager at Lyft's data division. I've been at Lyft for over 2 years. And today I'm going to talk about how we use Anomaly at Lyft for performing anomaly detection in real time. And I'll cover why performing anomaly detection is important for our business, how Anodot helps us to monitor our metrics at scale, what high-level architecture we're using with Anodot and AWS, and also some key takeaways we had after working with Anodot for over half a year now. So first of all, we are a physical business in that we are operating in physical world. We are actually moving people, and we operate on multiple timescales. So on a secondly basis, we are making decisions of matching passengers with drivers. On a minutely basis, we are setting the prices, meaning adjusting our prime time algorithms to match supply and demand levels. On an hourly basis, we could be applying market levers. So we could be offering some incentives to the drivers or discounts to the passengers. And then on a daily and weekly basis, we're performing budgeting. So we are allocating budgets for marketing, again, for driver and passenger engagement. So there's a lot of complexity on different timescales that happens within our business. And the same applies to the geographical dimensions. So we operate in over 300 cities, and that maps to over 13,000 of zip codes and over 300,000 market areas in which we could be adjusting prices or offering incentives for the drivers. So there's a tremendous amount of time and geographical complexity that we are operating in and have to monitor. So, but that aside, if we consider just 100 top market and product metrics that we would monitor at Lyft regularly to understand how we're performing, and we multiplied that by a number of CDs we want to monitor those metrics for. We get over 30,000 metrics that we have to monitor, and we simply don't have that many people to do it all the time. So this is where Anodot actually comes into play, and the solution to the problem is to only make people look at the metrics when they deviate from the baseline or from the forecast. In this case, you are not wasting time looking at the numerous dashboards and charts just to check if something is going according to the plan. You're getting proactively notified whenever things deviate from the plan. So I'd like to walk you through a real case that we had with Anodot, where Anodot helped us detect a real problem in our system. So some time ago, we shipped a new feature for our driver incentives service. And unfortunately, that feature unknowingly broke the integration with our billing platform. So with Anodot, we are monitoring every single line item that comes through our billing platform. That doesn't mean that we're sending all line items to Anodot as they are. We're sending aggregates. So basically, how many line items of each type we're billing against passengers or drivers in a given region with other metadata on a minutely basis. So Anodot helped us detect that something was going wrong with a particular line item, and what was going wrong is that the numbers that we were billing, the count of line items that were going through the billing system was way below the expected value, and then ultimately plummeted to 0. So that helped us understand that something was going wrong and then escalate the problem to the appropriate teams. And interestingly, when we were doing a post-mortem on the investigation, we found that Anodot was able to detect the deviation in this metric before the bad code, the bad pull request, was rolled out to 100% of the production machines. So Anodot was able to, if you see this orange line, so where it starts to deviate from the expected value, so this is where we rolled out our change to Canary, is where the production services get 1 to 3% of the traffic. So that illustrates the power of real-time anomaly detection system and how early you can detect deviations and problems in your business. Now, in this particular example, we had one problem. I was unfortunately the only person who received this alert, and I obviously am not managing the billing platform. And it took me some time to actually figure out what is the appropriate team and people that I should escalate this alert. And fortunately, I was able to reach them in time. But in many cases, useful alerts that are generated by Anodot are not reaching appropriate people, and I'll be talking about this in the key takeaways. So this is a high-level architecture that we're using for sending metrics to Anodot. So at Lyft, we're using AWS Kinesis as a mechanism to work with the real-time events that are collected from both servers and clients. We have a microservice architecture, so we have a tremendous number of the generators of those analytical events. And events could be anything. They could be registering, as I mentioned, line items that are billed. They could be notifying us that a ride was requested by the passenger. They could be notifying us that a passenger opened the app, and so on and so forth. So for actual processing of events, we use a streaming compute engine, Apache Flink, that we roll out on AWS as well. So Flink helps us aggregate the events in real time by certain time windows. So for certain events, we're using 1 minute time window. For certain, we use greater windows. But we found minutely window the most useful because we can then roll it up in Anodot anyways without losing the granularity. So the second up listens to those aggregates and then batches the metrics and then sends them to Anodot API. Anodot API was quite straightforward to work with. The only thing that we had to account for is the query per second limitation. So we had to provision that for that in our code. An important aspect of rolling out anomaly detection at a big company, which is Lyft, is to how do you make it easy to publish new metrics? So we have all sorts of events, all sorts of use cases, and many teams that are interested in performing anomaly detection. So if we were to ask them to write Java code and submit it to Flink every time that they would need to create a new metric, that wouldn't get us any good adoption in the company. So what we did instead is we created this simple configurable interface that users can use to submit new metrics. So in this case, what we're doing is we're specifying what particular event we want to aggregate and send to Anodot, and the aggregate here name is counter. So it's very intuitive. We're basically counting client actions, and then the dimensions signify what properties we are aggregating those events by. So in SQL terms, that means count, event, client action, group by OS, app version, action, and result, which could be failure or success. And so these configurations allow us to ship new metrics into Anodot really easily, and that helps scale the adoption. So we don't have to actually write any specific code unless we need custom filters or any custom business logic. The things that we also found helpful to configure is the buffer. So basically how much time we wait for events to arrive before sending them to Anodot. And that helps us control for late arriving events. For example, if the difference between event occurring, let's say on the mobile app, and the event being ingested by our systems is large. So finally, some key takeaways that we had from working with Anodot. So first of all, you have to start with a defined use case. What it means is you cannot treat Anodot as a magic black box that you send all your data and you expect it to find what's going wrong with your business. You have to come up with a real business use cases. For example, I want to monitor line items in my billing system because sometimes when systems break, I know that some line items can stop being billed, or I want to monitor IP addresses that users use to register for Lyft, and an anomaly in a particular spike in a particular group of IP addresses can be a signal for a fraudulent activity. And so when those use cases are a prerequisite for turning on anomaly detection, then we found that the implementation is much more successful. Second, ensure that you have a proper escalation policy. What it means is Anodot is really good at finding anomalies in data, but you also have to make sure that those anomalies find the right people who are actually responsible for those metrics and can make decisions, can investigate and take action. And those anomalies should find those people really seamlessly and as fast as possible. So as I mentioned in my example with the line items, we clearly had a challenge with the escalating the alerts to the right people that we had to solve. And it's especially important in large organizations where you have multiple teams, multiple owners that are changing. So at Lyft, we found that for some teams, email is the best channel, and we subscribe a team, basically a mailing list to an alert. For some teams, using our chat app is the best way to reach them. So we basically subscribe the whole channel in the chat app to Anodot alerts. Next, false positives are unavoidable. So anomaly detection is a hard problem, and you're always going to navigate this trade-off of being too sensitive and having too many alerts, or being overly conservative and missing something important. We found that it's impossible to only get alerts which are actually represent bad things that happen with the business. The trick is to find the good ratio. So in my personal experience, maybe a ratio of 5 false positives to 1 actual problem is a good one, because you can always skip through charts and alerts that look suspicious and then just tell that they are not actual problems. And then finally, start small and then expand. So Anodot makes it really easy to send metrics at scale. So you, let's say, turn on all these counters and you segment them by multiple properties, and now you're monitoring, let's say, ride requests by ride type and by region and by something else. But a lot of the times, if your metrics are too detailed and there are too many of them, it's hard to actually fit a particular use case. So we found it useful to start with maybe a less granular metric, and then if that's useful, increase the granularity, meaning adding additional properties to segment the metric by. And then it helps users to really get a good use of Anodot as an anomaly detection system. So with that, I'm going to wrap up my presentation, and I'll be open to answer your questions in the Q&A. Thank you.
Well, thank you very much, Gleb and Ira. Ira, we have a few moments before Q&A, about 5 minutes for a demo. We want to make sure the questions are coming in, and this will actually give our attendees a little bit of time to add questions if you haven't already. But do you mind giving us a 5-minute demo?
Yeah, definitely. So give me control, and I'll demo it. So what I want. So Gleb showed you. I hope. Let me know if you can't see my screen. If I hear nothing, then good. Good. So Gleb showed you an example of an incident that they had at Lyft, and obviously it's hard to share, full incidents with the world, because these usually are indicating of issues, although not all anomalies are issues. So let me describe a flow of how a lot of times people use Anodot in the context of a demo. So what I'm going to show right now, I'm starting actually with an alert on an anomaly that happens with a ride-sharing application. And here, what we see in the alert is that the title says that there is an increase in ride cancellations. So there are more ride cancellations. Now the question is where? So what we see here is one metric of measuring ride cancellations in a certain version of the app. A user is trying to get standard ride in LA using mobile Android devices. So again, you see here the actual measurement. You see the normal range of the metric as being computed by the algorithm, and then the anomaly that happens. And this is a fairly dramatic anomaly. Oftentimes, it's not as dramatic as Gleb showed, but you can still capture it and get alerted on it immediately. But it's not just about riders in LA trying to ride standard rides with using Android devices. Also, riders in New York are experiencing. You can see more cancellations from them on shared type rides, the same app version, Android devices. And you can see premium users trying to ride premium rides on Android devices. So it's obvious there is something going on. There is a lot more cancellations. Now the question is, can we figure out what it is based on what's correlated with these anomalies? So basically, at this point, you go and investigate this anomaly in Anodot, and this is this anomaly in the Anodot interface. So what you see here are all the different metrics that were correlated together. You can see them graphically charted and see the anomalies in them. But because we can correlate many different metrics together. In this case, there are 25 of them, but there could be 1,000 of them or 2,000 of them together that describe an incident. You have to really summarize so you can make out what they mean. So for that, we build a heat map called an Anomap, where we show you the dominant dimensions for each one of the KPIs that were anomalous and correlated together to one incident. So the ride cancellations that we were alerted on, we can see that the dominant dimensions are the version of the app and the type of mobile device being used, in this case, Android device. But we also see that at the same time, there are anomalies in the request wait time for rides. So how long do people wait until they get a driver that says, I'm going to pick you up. So that was anomalous as well for the same version of the app, Android devices. But there were other type of KPIs that were correlated. There were HTTP errors, so these are more technical. There were errors in the driver request API, and there were also decrease in the number of rides completed. So if I click on it, you'll actually see that the anomalies in the ride completed was decreased. For whom? For users using this version of the app on Android devices. So that gives you a very strong indication on what happened. There is more cancellation, and it looks to be something that that potentially is related to errors in the APIs. So these type of metrics. So they wait for a longer time, and there are more errors for the driver request APIs. So it's very strong indication that it's a technical issue happening, and maybe something with the API with the drivers. What we also do in Anodot, we also correlated with events that may be sent. Events could be campaigns happening, it could be holidays, but it also can be deployments of new version of the app. And in this case, actually, we can see that there is an event that is correlated with this anomaly. I'll click on it and it gets filtered. And this event actually describes a deployment that happened just before these cancellations started happening for one of the APIs. Basically the API that looks for drivers next to riders, near riders that are requesting rides. So there was a change in that for mobile devices, and obviously when we see more cancellations on Android devices for this version of the app, it's clear that this change probably caused it. You can go to your R&D team, the relevant R&D team, and have them fix it so everything goes back to normal. So this is really, in short, one flow of how to work with an anomaly detection system, get alerted, either via mail or Slack or PagerDuty or on any other type of system that can show you alerts. Then you investigate it to understand what's going on, what's correlated with what, and then you can go and fix it or take advantage of an opportunity that the anomaly signifies. So with that, we can go back to the presentation and to the Q&A.
Well, thank you so much. It's really helpful to see that. So let's get to the Q&A. We have quite a few questions that have come in, and I'd love to have those addressed. They're coming both for Lyft and for Anodot. First of all, I said this at the top of the hour, it's easy to miss. The first question coming in multiple times, are you planning to share these slides? Yes. The PowerPoint presentation will be available through Slideshare, along with a recording of the webinar on YouTube through an email that will be sent 2 to 3 days after the conclusion of this event. So keep an eye out for the follow-up email that will be sent to the address that you provided to attend today's event. Next up, does the data have to be in time series for finding anomalies?
So at least at Anodot, yes. There are other types of anomalies that may happen in different types of data, text data or more static measurements. These are different types of anomalies. So at least using the Anodot system and the type of problems we're trying to solve in terms of business incidents and autonomous analytics in terms of what's happening with the business day-to-day, time series is the way to go.
Okay, next up, and I'm just going to rephrase this slightly, if you're getting a lot of the same anomalies, he's given the number 84, which I don't know if that has significance. If you're getting a lot of the same anomalies, wouldn't the algorithm eventually pick it up as no longer an anomaly, but an expected occurrence?
It's a great question, and it's all a question of frequency. So a lot it depends. So for example, if something is an anomaly and it happens at regular intervals, then the algorithm will pick up that this is a seasonal pattern. So it has some regular frequency to it, and then it will learn this is a regular anomaly. If it's something that happens, at irregular intervals, and there's really no way to say that this is not an anomaly, except for so the approach is to actually have the patterns reduce, have the patterns reduce in significance, and then it becomes a very insignificant anomaly. If it happens frequently enough, then the algorithm will learn that as a normal pattern and will take advantage of it. So it really depends on the frequency of it happening, whether it's regular, irregular, and then if it's irregular, how frequent does it happen?
Ira, didn't you have a name for that when a pattern, when an anomaly becomes a recognized pattern?
Yeah, so seasonal pattern, that could be one of them. Oh, and of course there is we classify the anomalies to different types, like transient or level change.
Right.
And then yeah, but that's a different aspect of that question.
Okay, fantastic. Now, next question. What kind of machine learning techniques are used? Supervised, unsupervised, hybrid? Thus far, the assumption here is that these are unsupervised techniques.
Yeah, so most of it is unsupervised because that's the nature of the game. Anomalies in general are usually unsupervised, and also it's an unsupervised learning problem. But the feedbacks actually that we can get from user behavior, and either direct or indirect feedbacks, actually allow us to make it more of a semi-supervised technique whenever those feedbacks are available. So, but we can't assume that we'll get feedback. So it has to be completely unsupervised, and feedbacks then can be leveraged, but not assume that they're always there.
Thank you. Next up, and I'm not sure I understand this question, but is there an application of sequential analysis in the Anodot system? Maybe you could help everyone understand that term.
I'm not exactly sure. I'm assuming that the question is, does the analysis happen in a sequential manner? And yes, it does. So we actually adapt the models that describe normal and abnormal with every data point that comes in for every single one of these KPIs. So that's when I showed the architecture and the centerpiece of it, and talking about learning on the stream of data itself. It's actually sequential learning. And there are various reasons for that, both scalability, but also being able to be robust and adapt to changes that are normal in the data. So without doing that, you actually, if you do batches of data, then it means that for the previous batch, you might be stale already. So you have to constantly adapt.
And I guess the way I'm reading that, if you don't mind me digging a little deeper, I mean, is there any kind of state that's involved between those judgments? In other words, are you looking for, bounds outside of, some kind of Gaussian analysis, or are you actually like preserving state between these readings?
Yeah, so we actually preserve state, and we found it very necessary. First of all, you can see, visually, it's clear that there is temporal dynamics to every one of these KPIs, so you have to maintain some sort of state about the dynamic, the temporal dynamic. We do that with models that are, so using a Gaussian assumption is just about the noise of a certain point in time, but you have to have a mixture distribution with the temporal dynamics associated with it if you want to really capture the changes that happen normally in this data. So it's another reason for doing things sequentially rather than statically, because there isn't, the amount of states that happen actually keep changing. You have to keep track of them.
Okay, moving on. I see that Anodot provides APIs. Does the customer have to do the heavy lifting of connecting data sources to Anodot and the cleaning and preparation of the data?
Mm-hmm. So we have a lot of APIs, but we also have a lot of data collectors, both that can be provided as agents, but also through our interface. So we can connect to any SQL database from our interface. We can connect to, we have a connector using Kinesis. Actually, Lyft has decided to implement it themselves, which is, fine, but you don't have to do that if you don't want to. We have a lot of ways to connect to the data really quickly. and do it on our side. And it really depends on the company and the type of data source and how much control you want to have on what you're sending and how you're sending it. So the answer is you can do both. You can do the heavy lifting yourself or not, or use our connectors.
Okay, next up. It seems like it would be hard to know to whom to escalate an anomaly, since part of the value that Anodot provides is finding unexpected things. And a related question here is, can I have multiple targets, such as country or client managers, depending on what's being monitored?
So I can answer that, or Gleb, do you want to take that one?
Sure. Yeah, so typically it's mostly an organizational problem rather than a product problem, as we think. In general, we do have people who are responsible for certain KPIs or certain systems. So really, when we are working on a use case and help them introduce an anomaly detection, we make sure that they subscribe the relevant stakeholders to the alerts. It is possible to escalate alerts via multiple channels. So email, Slack, webhooks, all are supported and really help us to reach the appropriate people at the appropriate through the appropriate channel. So basically, it's just a process question of how we make sure that alerts don't get turned on without the relevant people subscribed.
And Gleb, we just have time for one more question here. If you don't mind my keeping the attention on you, why didn't you just build this yourself?
Yeah, absolutely. So anomaly detection as basically it's a hard problem because it involves, as I already described, a lot of challenges with time series forecasting. So we do have capabilities of doing that at Lyft internally, and we do this for very niche use cases such as forecasting our KPIs and adjusting them for market interventions that we are doing. For example, what will happen to our projected rides if we run this marketing campaign? And that's a very hard problem, and it's different from, I would say, a generalized anomaly detection for other use cases that are simpler. So we found that if we were to start building a system that would be universal for all different use cases and metrics at Lyft, it would take us a lot of resources that we would rather spend on something which adds to our unique value. And Anodot is a really focused vendor that helped us solve this problem because we just send metrics to them and we don't have to worry about storing them, running all the algorithms, escalation, tuning. So that we found really helpful, and that allowed us to really roll out the anomaly detection capabilities really fast. Otherwise, it would took us much longer time, and that would be a questionable investment in terms of allocating resources.
Thank you. Thank you so much. Thank you, Ira. Thank you, Gleb. And thank you all for attending today's webinar. Please remember to stay connected and complete the brief survey at the conclusion of the webinar. We look forward to supporting you in current and future projects. Thank you again, and everyone, have a great day.
Thank you.